Hello and welcome back. I hope everybody's having a good experience learning about how to use JMP and do data mining. In this video we're going to look at problem number 6.1 from the textbook and work through that in detail, and hopefully that will help you with the homework that you have and help you understand better what it is we're doing with data mining. So pull up the Boston housing data set. What we're interested in is the median value, this variable here, and we have lots of variables that we're going to use to explain that. We've talked about this in class already, and so hopefully you're up to speed on the data set. Part A says, why should the data be partitioned into training and validation sets? That's kind of an easy question now that you know a little bit about what's going on with data mining, and that is that we fit models on the training data and then validate them and pick between the different models that we fit on the training data set with the validation data set. We're going to make a validation variable by going to Analyze, Predictive Modeling, and then Make Validation Column. And this asks us, first of all, which values we want, and we'll just select all of those. Say OK, and then we can put in 0.6 and 0.4, and we can change the random seed right here if we like. I'm just going to leave it as is. I'm going to say go, and then you see the validation column showing up here. That's not necessarily the same one that you're going to get or the same one that's in the rest of this video. So now we've got our validation column. Move on to part B. Fit a multiple linear regression model to the median house price as a function of crime, Chaz, and room, and then write down the equation for predicting the median house price from the predictors in the model. So to do that, we're going to go over here to Analyze. We're going to say that is median value is the Y, crime, Chaz, and room are the X's. Validation is validation. And we want to do standard least squares model. And when we do that, we get this output that says the intercept term is -33. Crime has a coefficient of -0.21. Chaz 0 has a coefficient of -1.9. And room has a coefficient of 9.2. So we're asked to write down what the equation is, and this is actually a little bit misleading because Chaz is an indicator variable. Typically when you use indicator variables, you just take this coefficient and multiply it by either a 0 or a 1. And I'm not sure why JMP does this the way it does. But if you look at the estimates and then show a prediction expression, you will see that this is actually a little bit different in JMP. And the way this works is you've got the intercept, crime times its coefficient, and now for the Charles River you have to say, do I have a 0 or a 1? And then if it's a 0, add in -1.91, and if it's a 1, add in 1.91. And so I would say this is non-standard. So how could we make this into the type of indicator variable that maybe you're used to? Well, let's come back to our data, and we're going to say right click on Charles River, column info. All I have to do is change this from a nominal to a continuous variable. And when I do that, go back to Analyze, Fit Model. I want to run the same model. Now I can drag all this stuff all over the place, or I can click Recall. It brings all this stuff in just as I had it, and the fact that Charles River has changed doesn't affect the model, the way I'm calling it, and so I can click Run. And now I see some similarities between these two things. Pull this one over here. What do I see? Well, let's actually look at the estimates. So what I have here are slightly different intercepts, here we've got negative 34, and here's negative 33. Coefficients on crime are the same, however, negative 0.21. Coefficients on room are the same, 9.2. And the coefficient on Charles River now is 3.83. And that turns out to be twice 1.91. And so in this model over here, all I have to do is say if Charles River is 0, then multiply by 0. If Charles River is 1, multiply by 1. And the difference between the intercepts is actually also 1.91. So for some reason, when you have a nominal variable that you're throwing into a regression model, JMP treats it like this. So the easier way to deal with this is to convert it over to a continuous variable. Now if we come up here and look at the save column options, and we want to look at the prediction formula, and that's going to be the same values that we get for predicted values. But there is a difference between these two, and use the formula if you want to score future data. And so I'm going to click on that, and just to show that we are really getting the same thing here for both of these, we'll also look at the predicted formula for that one. So we come back to our data, and now you can see that the predicted formula has been added, and these numbers are all identical. So for part C, we're asked to use the regression equation that we just came up with to predict the median house price when there's a house not on the Charles River, has a crime rate of 0.1, and there are 6 rooms in the house. And that is the reason we use predicted formula here instead of just the predicted value. And so let's go down to the very bottom of the data set, and we're going to go over to crime, and we're going to basically add in a new data point. So we put in a 0.1 for crime. Charles River is 0, and rooms are going to be 6. So now when I come over and look at the predicted values, you see this has been populated automatically, and that's because I use predicted formula instead of predicted values. So that's kind of nice. That's one way to do this. There's another way to do it, and that is if you come over here and click on this red triangle and then go to factor profiling profiler. You can come down here and click on those red things, red numbers, and put in 0.1, 0, and 6. And when you do that, you get the same value, 20.26. What we had over here, 20.26. So multiple ways that you can do that. And if you had a whole bunch of data, you could just augment that here, and that'd be the easier way to do it. The last part of part C says what's the prediction error, and that actually is a kind of a trick question, and trick questions are only fun when you're the one asking them. Why can we not calculate the prediction error here? Well, because we don't know what the actual value is for the median value. If we had that, we could calculate the residual or the prediction error, but we don't know what it is, so we can't predict that. But we can do other things to help us understand that. If we come over here and click here and go to save columns, you'll see that there's a mean confidence interval and an individual confidence interval. So the mean confidence interval is confidence interval for the mean. The individual confidence interval is really the prediction interval for an additional observation. If you click on either of these, that's going to give you basically the same format as this predicted value. It's going to give you numbers that are not going to be changed. But if you click on the formula, that's going to give you values that you can update or calculate for your new data. So let's do that one, and then we'll also do that one. Come back and look at the data. Now you see we've got 95% interval, confidence interval for the mean of the median value, and this is going to be somewhat narrow because we're talking about a whole population, and so we're 95% confident that the mean value is between 19.45 and 20.07 when crime rate is 0.1, Charles River is 0, and there are 6 rooms. So that's the average value for that situation. But the prediction interval for an individual value is much bigger. You can see it goes from 8.5 on the low end all the way up to 32 on the high end. And what this is saying is if I were to take a single observation in the future that I don't know what what the true value is and I wanted to estimate it, then this is my 95% confidence interval. And because we're talking about just a single value, that's going to be larger than when we talk about the confidence interval for the mean. Okay, so that brings us then to part D, which says consider the 12 predictors. Which predictors are likely to be measuring the same thing among the entire set of predictors? Discuss the relationship between indus, NOx, and tax. And if you think about the indus, it's the proportion of non-retail business acres per town, and usually they're the ones that are producing pollution. And so NOx is a level of nitric oxide concentration, which is a pollutant. And these types of places also pay higher taxes than residential properties. So we could make an argument that we don't need all 3 of those. We could get away with just using potentially 1. Part 2 says to compute the correlation table for all the data.
We're going to go to Analyze, Multivariate Methods, Multivariate, and we want to select all 12 of the predictor variables. So that's CRIM all the way down to LSTAT. And we're going to say make those our Y columns, and then we're going to say OK. And it tells me that one of these is not continuous. That's okay. We're still going to look at it. And so here we get the correlation matrix with the scatter plot matrix. And we can see down the diagonal the different variables. We were asked in part 1 to compare indus, NOx, and tax. So if we look at indus versus NOx, you can see there's a pretty good relationship there. A lot of the information contained in indus is also contained in NOx. And let's scroll down a little bit so we can find out which one is tax. Tax is here. So tax versus NOx. Well, there's maybe not as much information going on here. Let's look at tax versus indus, and yeah, that looks fairly linear. We could look at the correlations to see exactly what the correlation is for each of these things. So indus and NOx has a correlation of 0.76. Yeah, so let's just look at it pairwise so that kind of gives us a better summary of what's going on here. So if we click on this and go down to pairwise correlations, you'll see here are all the pairs, and the correlation over here is also given to us in this column. And this is not that helpful in terms of trying to find the big ones. But if we rank sort this, so right click on correlation, sort by column, sort by correlation, say OK. Now we see that tax and rad have correlation 0.91, and then NOx and indus 0.76, tax and indus 0.72, tax and NOx 0.66.
Part 3 says that we need to run an exhaustive search on all the variables. So we're going to go analyze, fit model, median value is our Y, we want crime through LSTAT as our X's, we want validation as our validation, and we want to go stepwise and then say run. And when we do that, we get this window, and if we come up here and click on the triangle, we see all possible models, and the maximum number of terms in the model we want to turn to 12, and the number of best models to see, this is set at 56, and I think what this is saying is it will show up to 56 models with the same number of variables. Let's just, for fun, change that to 10. And we say OK, and here's what we get back. Models of size 1. We know that there's more than 10 of these things, but here we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We see 10 2s, 10 3s, 10 4s, and so forth. So we're not seeing all of the models, but we're seeing the top 10 for each different size. And we don't see malloc CP here, so if we right click, go to columns and add in malloc CP, you'll see that shows up as well. And now we want to pick which model is best. So how can we do that? Well, we have to decide which criteria we're going to use. And we could use malloc CP if we wanted. So let's sort by malloc CP, ascending. And we see, according to malloc CP, we have the number of variables, the number of x's is 10. So that means 10 plus 1 is 11. So malloc CP, this one looks like it matches best. This 11 and 11, and then finally 12 is the best one after that. Malloc CP is always going to be equal to the number of parameters when you have the full model. But this is suggesting that these three models are the best. We could also sort by root mean square error. We want that ascending. And when we do that, we get a different model for the best one. 11, and then 10, and then 12. What else could we sort on? We could do AIC, smallest to largest, and this one takes us back to the original ordering that we had. So based on CP and AIC, these three models look like they're the best. So we want to now look, and this is all in the training data, so now we want to look at the validation data set and see how they do. In other words, we want to come up here and look at the R squared on the validation and the RMSE on the validation. So if I just click right here, it will tell me that the model without indus and age is the model that has the best malloc CP and the best AIC. And when I look at the R squared value on the validation set, it's 0.6854. Root mean square error is 5.06, which is bigger than the on the training data set of 4.67, which is to be expected. If it were smaller, that would actually be a surprise. If I want to compare that to the next model, I just click on the next one, and what do I see? The validation R squared goes down a little bit. Yeah, goes down, and the RMSE goes up. So this suggests that, yeah, this is in fact the best model of these two. Let's look at this next one as well. And we see same sort of thing. RMSE is a little bit higher in the validation set, and R squared is a little bit lower, but not much. And that's one of the things you want to take away from this. There's a lot of models. There's lots and lots of models, and how different are they really? And so to say that this one is absolutely the best right here, that may be a stretch actually. It's the best that we've been able to identify, but that doesn't necessarily mean that it's the best model out there. But given the error structure that we have in our partitions, this is the best model. If we were to redo the partition, we might very well have a different model that does better. So that's all I got for this video. We will see you guys in the next one.